Здравствуйте,
Oh,
I think. And that's it for my Russian. So yeah, I work on a Linux platforms team at Cisco, and we're specifically focused on shipping Linux that's very one application specific. So this runs on exactly one box. It will only ever run application. There's a lot of, it only ever does this one thing. And so it turns out that if you're a kind of a major distribution, you have to support everything. So you have some user, and he has a floppy disk because he's an ancient user, and he puts it in his floppy drive, and if you are Ubuntu or Red Hat, you expect that user to be able to use his floppy disk. And if he can't, then he gets very angry. And then he'll probably throw your distribution away and try some other distribution where the floppy drive actually works. And so you are, every one of you that's running just a regular distribution kernel has a floppy disk driver in it. And you think, okay, well, the floppy code is very old, it must be very mature. Certainly there's no big bugs in it, so what's the big deal, right? But it turns out there's actually still, people are still finding CVEs in even the floppy code. This is, relatively recent. These things were found this year or last year. Probably the bottom one is maybe the most serious, but there's some other info leaks and stuff. So people can exploit that code that's sitting in your kernel right now. And who knows how many of these also exist. In fact, when I saw this one at the bottom, I went and started looking at other old code, and just by looking at the code with a clever grep, I found some other instances of information leaks in the kernel that we ultimately fixed. So this is, you're running a lot of old code, or maybe not even running it, but it is in your system, and you don't necessarily want that. So, so what do? You basically just delete the code. So of course we can't delete this code from the kernel tree because other people care about it. But me, as a guy who's shipping an application-specific Linux, I know that nobody's ever going to use a floppy drive on some Cisco piece of hardware that we ship them. So in our kernel, we can just comment this out. We can just disable this particular configuration. So since we're not general purpose, and we know we don't need most of the hardware support, we don't need floppy disks, we don't need that kind of stuff. We also don't need most file systems. So there's a lot of maybe bugs in file systems or whatever. We can eliminate most code. There's a lot of these. So we don't need sound, we don't need wireless, we don't need all the staging drivers, we don't need Bluetooth, we don't need battery stuff. We don't need, I don't even know what cyclades is. But like, these are all examples of things that we don't need. Actually, there's a lot of these. And I just stopped here because you have to at some point. I could have just done this for 2 hours. But like, kernel configs are thousands of lines long, and you can just disable almost everything. And so the first sort of lesson for us is we started with a distribution kernel. But most of this stuff we don't need. And in particular, at Cisco, we have this whole process, and I guess most large organizations are like this, where there's some external security team, and when that external security team says, hey, there was a bug in XFS, you guys need to fix it, it's like hair on fire, everybody's, oh my God, this is terrible. But if you have XFS disabled in your kernel, then you just write that guy back and you say, actually, this isn't a problem for our product. And that's a lot more fun to do than it is to actually sit and fix the bug. So while this is a lot of work to go through and kind of painstakingly do this, it's proactive. You can do it. You don't necessarily need to. You don't necessarily need to wait around. And then when that guy comes to you and says, "Here's a bug," you can say, "Not a problem for us." So the kernel can. So there's another set of things that you can do. And this is by a guy actually. Alex Popov, who's based in Moscow, but there's a number of other sort of hardening knobs that aren't necessarily disabling functionality, but it's changing things like the base mmap address and other things that are commonly used in exploits And so he has a very nice script to suggest these sorts of things. And one of the things that it suggests is this config option static user mode helper. How many of you have heard of this? The one other guy, yeah. So this is an interesting one, and I want to do a deep dive on this just because it does fix some real problems. But to do that, we're going to have to take a little detour and find out what a user mode helper is. So the kernel, this sounds weird, but the kernel actually asks user space for stuff. So you're used to asking the kernel, hey, can I have more memory? Hey, can I do this I/O operation? Hey, can I do whatever it is? But the kernel actually, from time to time, will ask user space for things. So if there's a hot plug event, the kernel wants to say, do something, so it triggers a user mode helper. It basically just runs a binary on the system. Power off and reboot. If there's a core dump, the kernel says, hey, this process dump core. It invokes the core pattern, maybe in the sysctl, maybe you've seen this. That's an example of the kernel calling into user space to say, hey, this bad thing happened, and now you got to deal with it. cgroup v1 has a notify on release thing where when the C group dies, you can set this path and the kernel will call into user space, call that binary and say, hey, this C group just died. Module auto-loading is done via this user mode helper stuff. And actually there's a whole, this thing that I wrote, I went through, at least for the 5.0 kernel, and just made a list of everywhere in the kernel where this happens, and just sort of tried to annotate, you know, how things are configured, and how like some of these are set via config options, some of them are set via sysctls, some of them are this notify on release file. Users can just echo whatever they want in there. So there's a kind of a mishmash of ways to do this. And so I guess just as a quick example, for module autoloading, suppose that you're this can be any unprivileged code. The kernel gives you access to its crypto library, so you can ask it. This afalg is a socket type that you can use to talk to the kernel and ask it to hash stuff for you and do whatever. So when you do this, if the module hasn't been loaded, net will realize, oh hey, I need protocol number 38. So in the kernel, it does this request module function, request this thing. That calls goes to a call mod probe function, which does this call user mode helper thing with the mod probe path, and then that actually executes this thing in user space that is the mod probe binary and says, hey, find this thing, and then mod probe looks in the module aliases and figures it out and loads the right module into the kernel. So that's sort of just like an example of how this would work. But you can attack this. So the most obvious thing is, if you think about what needs to happen in this mod probe call, it needs to load a module into the kernel. So when this call user mode helper function, that runs everything as real root. So in particular, it has all of the capabilities. It has all of the rights to do everything. It runs this in the initial mount namespace. So this is a pretty privileged operation. When the kernel calls this, that's basically as good as it gets. And this thing is settable via a sysctl. So that means if you could somehow control that path, all you need to do is trigger some kind of module autoloading, which, if you ignored my advice in the first part, you have a ton of code sitting around. It's very easy to load random protocols that nobody ever uses. It's very easy to trigger this, and you can, by and large, trigger this as an unprivileged user. So if you set this via a sysctl somehow, you can then have code called as real root however you want. So you often will see on the kernel mailing list, people are concerned about binaries that function like a setuid_cat, because if you can trick a binary into writing something into a file, writing content that you control, you can exactly use this to then exploit the system. So that's an attack, but now people have been concerned for a long time about both making sure binaries don't function as a setuid_cat, but also just locking these types of things down via like LSMs and other things, making sure the path is protected and whatever else. So there's I guess a more sophisticated attack, which is if you can get some shellcode into the kernel, you can use this to call back into user space just directly. So you might think, oh, I have to change some permissions on some structure. Like I want to edit my current task's struct cred so that I get root or whatever. Maybe I have to set up call commit cred 00 or whatever. You don't actually have to do that. And there's a couple of examples of people doing this in the wild. There's this Project Zero blog post is by Jan Horn, and he talks about you actually really only need control of 2 registers in order to make this happen, which is a lot less control of things than you might otherwise need. And there's a couple other exploits where people use it in different ways, but ultimately the goal is really to run some code as root on the system, and this is a way that you can accomplish that. So what do we do about that? And it turns out there sort of already exists a solution. So this thing I talked about earlier, this config static user mode helper, this is a kernel option that was added actually quite a while ago. I think maybe 2015 or 2014 even. It's quite old. And it's, again, Alexander Popov's hardening script recommends that, that you use this, but it's near as I can tell, people don't really use it. So what does it do? It proxies all of these invocations of this thing as real root through a hard-coded path in user space. So this is hard-coded in the kernel config. So when you build a kernel, the path is there. Nobody can change it. It's in read-only memory. So you always call this other binary, and then that binary gets to decide, is this a reasonable thing to execute or is this not reasonable? And you can imagine that you may look at the thing and see, okay, sbin mod probe is reasonable, or the hot like udev things are reasonable, but this random code from /home that some user wrote into their home directory, maybe I don't want to run that as root. So what goes in this? I did actually, while I worked at Docker, I did a first implementation of this that was just a really simple C program that basically just denied everything. It ran mod probe and a few other things, but everything else it denied, which was fine for Linux kit when I was working there, but it's actually not general purpose. And so I looked around, and there's one other person in this room who has heard of this. Turns out people don't really know about this, and it's sort of a simple thing that you can do to harden your system. And I was kind of amazed that nobody else had written an implementation of this. So then I wrote one, and like a true guy with tight pants and a beard, I hipstered out and I wrote it in Rust. So it's actually quite small. It's 200 lines of Rust. And there's a config file that you could specify what to allow. And one of the reasons that writing this in Rust is because if you're parsing a config file, there are bugs in parsing. Rust is very good at doing things like this. So it sort of seems like a natural choice, but it's also kind of experimental to be shipping stuff in Rust. Actually, I was talking earlier just about maybe if we wrote something and put it in the kernel tree, maybe people would understand how to use this more, but then it would probably have to be in C. So mostly the point of this talk is just to tell people that this thing exists, and if you want to write your own implementation, do it, but this can make your systems better. And that's sort of the goal of this. If anybody's interested in putting something like this in the tree and they have a better way than, trying to get a whole Rust compiler infrastructure in the kernel tree or whatever, I'm all ears. So just kind of a brief overview of how it works. So the kernel does this thing where it does a call user mode helper, but the first argument there it says mod probe and then mod probe whatever else. So the user mode helper has a hard-coded config path, at least what I did this first implementation. And so it reads this config file and then decides what to allow based on what arguments you have or have not passed it. And then it re-execs the real binary if with the actual arguments and things, if it was really okay. So some sample config here. This is, again, just some Rust likes to use 2ML, so I wrote this in 2ML, but it's pretty flexible. But you have mod probe. Mod probe is typically called with 4 arguments, so we allow up to 4 arguments. Reboot is just this one binary, but it's settable via sysctl. So if you set that sysctl, then you'd have to change this config. There's some other stuff here. The U event stuff and whatever. This is sort of just as an example of what this thing might look like. So at this point, we should probably talk a little bit about what the threat model is. So like I said before, this blog post by Jan Horn points out that you actually only need control of 2 registers in order to make this call. So any exploit that has control of these 2 registers can run code as root. So that's sort of where that's the threat we're trying to protect against. There's other situations where the attacker can write to control the sysctl or whatever. We don't consider those, mostly because if they can write, maybe if they have a setuid cat binary, they can also just overwrite the user mode helper with whatever they want, or they can overwrite the config file, or they can there's a lot of things that they can do. So this is really, if you're already in the kernel, you have control of these 2 registers, this is the threat that this thing protects against. You could maybe argue that, hey, if we don't allow any configuration at all of this thing and we hard code it all into the binary, then we can maybe get rid of, okay, well, if they can write to etc, then it's, we can protect against one more thing, but honestly, it all seems, it seems like maybe the thing that you're working on protecting against is this first part. So there's some to-dos. I mean, this basic implementation kind of protects against the most basic thing, but you could imagine if there's a bug in the actual implementation of mod probe or whatever, if there's somehow you can exploit that, maybe you want to protect against that temporarily because, I don't know, it's hard for you to upgrade, so you could do some argument filters. There's this special bit that the kernel has that's called no new privileges, so if there's an exec somewhere that you can't exec into more privilege than you already have. Maybe that would be interesting if, for example, you did some other things like add some namespaces, so maybe the user mode helper would run something in a particular namespace so that even if there's some bug in the program, it can't get out. All this sort of seems, it's fancy, that you could add setcom filters and stuff. This is all very nice, but really the core thing that we're protecting against is the fact that you only need control of 2 registers. So I don't know if this is really real to do. Again, if anybody's interested in collaborating on putting something in the kernel tree, maybe we can talk about what other features would go in there. So there's some pain points with this. I mean, the first one is now instead of one place, when you set the mod probe path, now you have to set it in 2 places. One is this config file, another one is the mod probe path. We could read the sysctls for these things. Maybe that would make this easier, so maybe that's a to-do. So you can imagine this thing just reads the mod probe path. If that matches what it got, then it allows it. Some of these things are settable via kernel config, so they're hard-coded and they never change. Yeah, so there's a few pain points here. It makes it a little bit more obnoxious to be dynamic. Like if you imagine the cgroup notify on release thing, people can write whatever they want in there, and then you have to change that in this config. That's kind of painful. But also, I don't really know that the cgroup systemd uses the cgroup v1 notify on release, but I'm not aware of a lot of other user space code that does. And systemd uses the same path for everything. So maybe this is okay. At least for us, for shipping what we're shipping, we know exactly what's supposed to be running and what's not supposed to be running. So for us, this is a perfect solution. So there's code. There's a detailed README about the threat model and stuff. And also I included, when I went through and I audited the kernel, I included a full config and tried to label, okay, this is set by this sysctl, here's this config option. So this, you can see everything, at least in 5.0 when I originally did this. You can see everywhere that it's called, and you can sort of see that I think there's maybe 20 entries or something. So there's a fair number, but it's not like there's not thousands of them. So it's realistic to try and make this list and do the right thing. Let's see how we're doing on time here. we're 20 minutes left, something like this. So I guess another thing that we do is we protect secrets in the TPM. So you can imagine if we're shipping some kind of private keys or something there, if somebody boots, some rogue kernel boots somehow, we want to make sure that that kernel can't read those secrets unless we're in a protected environment. So this is maybe something that general purpose things don't care about, but again, if you're shipping an application-specific Linux that has some of these secrets, you don't want people to be able to read them out. So the problem statement is we store some secrets in the TPM. We want to restrict access to those secrets to authorized kernels. And the rub here actually is this third one. It needs to work on both legacy BIOS systems and UEFI-based systems. And it should be easy to manage and handle updates gracefully because we do ship a fair amount of updates and we change kind of how things are configured here. And so I sort of am going to assume some base level of knowledge about TPM, but basically what it does is you can seal data and in a set of platform control registers, I think is what it's called, or something like that. So you can use a specific value of a PCR to unlock particular TPM secrets. And the TPM is sealed in epoxy on the thing, on the motherboard, so you're not supposed to be able to physically tamper with it. So this is sort of the basic trust module for things. So when you typically do like a secure boot would measure the system state, maybe your bootloader or whatever, any firmware like on your wireless cards or whatever's in there, kernel command line, and it would measure some state and go into the PCR. And then you, as a kernel, you have an expected value. You know that, oh, I expect the value in that PCR to be whatever it is. And so when something like this changes, if somebody loads a different kernel or somebody updates the firmware or whatever, when the components change, then the PCR values change. So that's how you can measure changes and figure out, am I in a healthy environment or not? So for UEFI secure boot, it verifies the signature of everything that it executes. So there's a static root of trust. There's a public key embedded in the firmware, and Microsoft controls all these keys. And this is sort of a technical detail, but it's PCR number 7. Each TPM, I think TPM 2.0 has like 20 of these platform control registers that you can measure stuff into, and it's by convention uses register number 7 here. But what this means is, since it verifies a signature and it doesn't actually verify the bits, this is stable across kernels with the same signer. Which is a feature, because then if I upgrade to a new kernel, all I have to do is have the same key to sign that kernel as I did before, and the system will boot up and say, okay, this is from the same signer, I'm in a healthy mode, I will continue on with execution. You can do, there's an alternative to this, which is Intel Trusted Execution Technology. I guess I should say UEFI Secure Boot is good. It's sort of what we want, except for it's UEFI only, and we have to support systems with legacy BIOS boot, so this will not work for our use case. So the next kind of something like this is the Intel Trusted Execution Technology, and this is shipped on more systems than Secure Boot, and it turns out that we got lucky, and all of the systems that we care about have this. So this is it's sort of a similar thing. The hardware and firmware create a dynamic root of trust, and it has this funny name. I don't know what that stands for. They have what they call a measured launch environment, which is roughly equivalent to what happens here. It verifies and bootstraps the kernel. But worth noting that this TXT thing, at least right now with the current implementation of the tool, it's different for different kernels. So UEFI Secure Boot has a stable PCR, meaning it's the same across different kernels as long as they were signed by the same system or the same person, but it only works on UEFI system. Intel TXT has unstable PCRs, meaning if the same person signs a different kernel, because the verification happens on the actual kernel bytes instead of the signature bytes, it's not stable, which means you have to do something more clever in order to make it so that you can handle upgrades, kernel upgrades, and stuff like that. But this is nice because we can actually use this with more systems than UEFI. So I guess the first lesson that we learned is the signature-based PCR thing is really necessary for us because we want to ship kernel updates, and I guess everyone wants to, which is why UEFI does it this way. And so the TXT verification of the kernel, and actually, I should have put this in parentheses or something. This doesn't exist yet. The initRD and command line happens in the tboot bootloader. So this proposed solution that we've been implementing, this is all work done by a guy named Paul Moore, who's on my team. You may know him as the SE Linux maintainer or libseccomp or other things. So he's actually working on implementing all of this stuff in the tboot bootloader. And what he's working on is using supporting signature verification using PECOF, which is actually a Microsoft execution format, but it's what UEFI uses. So again, for us, the goal is eventually to deprecate all the systems that don't have UEFI, so we can switch to UEFI boot, so we can do a bunch of other things. So I think the idea here is that using PECOF, we will be able to upgrade quicker. The other thing that is very important is no changes are required to this SNet ACM thing because that's in firmware, and we basically can't change that. So that's the way that we're proposing this solution. And actually, I don't know if let's see. I guess I can go through this quick. I only have a little bit of time left, but so the way that this the way that the flow happens, the bootloader boots into tboot, and then tboot does this special instruction that goes into the SNet the authenticated code module. That's what it stands for, and that establishes the dynamic root of trust. It examines this LCP, this launch control policy. This is all sort of in the weeds a little bit. So this launch control policy, you hard code in the TPM, and you say, I only want tboots to run that look like this. So that thing validates the firmware that you've shipped. It validates the tboot that you're about to run, and then control flow is transferred back into tboot. Tboot continues to execute. It's in this protected environment. It knows that it's exactly the right tboot, and so it changes the TPM PCRs to that state. It continues to execute. It does whatever kernel command. This is the PECOF verification of command line, kernel initRD, all that kind of stuff. And it's currently using the hash value, so it's not stable. But I think Paul's working on, as we speak. Adding support for signature verification. So tboot extends the PCRs to the right state. They're protected against tampering because the thing's covered in epoxy. So now when the OS boots, it can read these TPM PCRs out and understand, okay, I am in a good state. I know that the kernel command line wasn't tampered with. I know that the initRD wasn't tampered with, and I know that the kernel itself wasn't tampered with. Which is the goal, because then we can unseal the TPM secrets and live happily ever after. So kind of where I think Paul's at right now, there isn't verification of the initRD or kernel command line. In fact, nobody's doing this today. UEFI doesn't do it. They have some workarounds, so we may try and work on that. But the existing digest verification works fine. He has some code. He's posted some mailing lists. This is the interesting like if you're interested in following this work, this is where it's at. He also has some slides. He's given a talk at LSS North America, and he will give another talk at LSS Europe in 2 weeks or whatever. So this is sort of, if you're interested in interacting with this, that's where you can find that. Thank you. And I will be happy to take any questions.
Thank you. Microphone. Thank you. Do you have questions?
Two questions. I'll start with the TPM. Would you please explain to everyone here how you're doing the change management of keys in TPM? I know, but explain to everyone here now.
It's painful, I guess, is the explanation. So we actually don't control the keys. There's some separate organization in Cisco that controls a private signing key and everything. So it's burned in, and if I think my understanding is basically if that key is compromised somewhere in Cisco, we have to fly a guy to your rack and fix it, which is unfortunate, but yeah.
Okay, when I wrote my two user mode helpers, the one thing that I really wanted was a filter for the modules that can be loaded, and I didn't solve this in your.
Yeah, so that's one of the to-dos is, argument filters. So you could imagine writing some argument filter that's regex based or whatever. And I mean, if you're interested in that, I don't think it's very hard to do. It's just a matter of, what's the right language for describing this. And again, if you were writing this in C, then it gets a lot more terrible. So especially since you want this thing to not be exploitable. So I would definitely be open, if that's something you're interested in, and if you're interested in using this, I'd be happy to implement it actually, because I don't think, Rust has good regex libraries. I don't think it's a big deal. But at least for me, it wasn't necessary for us right away, because we don't even ship modules that we don't want to load. So yeah.
Okay, here's the next question.
So please correct me if I'm wrong, but if you already have some program running as a root, I mean the attacker has access to something running as a root with the capability to ptrace other processes, then the whole stuff related to user mode helper is totally invalid, because you can always ptrace the user mode helper and modify it to run anything else.
Yes. Yeah. So if you are already root,
Yeah, but you may be root, but without the capabilities. And if you are able to ptrace the user mode helper, then you still can escalate your privileges.
But
yes,
yeah, ptrace is a pretty strong.
That's a precondition. Yeah.
Yes.
Yeah.
Yeah. If you can ptrace that, you can probably also ptrace a init. Like you would have enough rights to ptrace a init. So, yeah, I mean, if you have control of ptrace as root, you've sort of already won. And we're not. That's not protecting. We're not protecting against that here.
Yeah, but in the very beginning of the talk, you assumed that we are able to execute a Cisco to modify the user mode helper path, or we have an exploit that is able to write to a kernel memory.
Right. So there's two attacks there. The exploit actually doesn't need writing to kernel memory. It just you just need control of two registers. So it's a much smaller. Basically, what this whole thing is protecting against that one exploit where you need the control of two registers. I totally agree that if you can write to arbitrary paths on the system, or you can write to kernel memory, you kind of that's it. So yeah.
Okay, thank you. And please keep thinking about the best question. The next one.
Are you using some specific frameworks like Yocto Linux to assemble whole system, or it's some homegrown scripts?
It's homegrown. So we are also shipping most things as containers, and so we have our own container infrastructure. In fact, one of the maintainers of LXC, Serge Hallen, works on our team. So we're mostly the root is thin, and actually we have some products where that's not true. But yeah, so we're not using any frameworks or anything. It's totally homegrown just because of it doesn't look really like any other Linux out there, at least that I've worked on. But I've only really worked for distro companies, so maybe that's a bad sample.
Okay, thank you. We have more question. Okay, see one.
Thank you for presentation. Obvious question here. If you use your keys in TPM only for running tboot, as far as I understand, it prevents to update any firmware on that hardware, right?
Yes.
So basically, it's brick.
Yeah. And like I say, I think our solution right now is we fly a guy to your place and have him fix the firmware. We do, like everybody else, I guess, we ship the, I forget what these are called, the microcode updates. But that happens actually in the init RAMFS. It doesn't happen early enough that tboot rejects it. So there is some small window where if you have a microcode exploit, or like, I don't know exactly how this would work, but I can imagine some small window between when the new microcode is loaded and when you're in this trusted execution environment that there might be some exploit there. But yeah, for other firmware for like RAID controllers and stuff, yes, you basically can't update that right now. We don't really have a good way for customers to apply that stuff anyway. Basically, if you have a problem with the firmware in your RAID controller, if that's something that we need to update, we just RMA the box and you send it back to us and we send you a new one. So it's a theoretical problem, but actually there's a practical problem of even customers have no idea how to apply a RAID firmware update in the first place. So it's not something we can do anyway.
Okay, thank you. Do you have any other questions? Looks like no, so now you need to pick up the best one
Best
to
question.
present this Tegma Cup.
The
The last one.
The last one.
Yeah.
Does anybody want a cup? I'll say. You know, American
Okay.
doesn't want the. So okay, then I'll go with the P-trace question. How about that?
Okay.
Is anybody who didn't ask a question?
It's your choice.
All right. How about the third question here? Andy, do you want one?
Yeah. I
No,
believe
really.
yes. Okay, so thank you very much, and thank you for your questions.
Thank you.
Thank you.